What's up, folks? How we doing? Just trying to hone some chill vibes here. Getting ready to do this chapter 4, the rest of it. You guys did your exam. Good stuff. We're ready to move on, folks. Okay, let's turn that down, Bob. Oh, Bob, I love you. Okay, folks, hopefully you have watched the first video I recorded on chapter 4. What was that, number 11? I've lost track of the numbers. And hopefully you also watched that short demo video that I shared for you. So normally that's a demo that I would do live in the lecture hall. I love that electrolyte demo. But it is what it is. So watch that video. I think it's really cool. And it really is showing you why we call something an electrolyte, right? Hopefully you gathered from that demo that when an electrolyte dissolves in solution, it can conduct electricity because there's a separation of charges, okay? So now we're going to really get into this, like discussing the difference between strong electrolytes and weak electrolytes, okay? So a strong electrolyte, there's several examples. Soluble salts, strong acids, strong bases. We're going to talk about what this whole soluble thing means as we progress, okay? A weak electrolyte is a substance that partially ionizes when dissolves. Okay, so what does that mean? Well, I'll give you an example. So HCl is a strong acid. Okay? Strong acid. And by saying strong acid, no, this isn't the stuff you take at Burning Man. There is a chemical definition of strong acid, okay? And that definition is that it completely ionizes when dissolved. So that means now this HCl aqueous, okay, when it dissolves in a solution, it completely breaks up into H plus and Cl minus, okay? So for example, suppose if I had 1.0 molar HCl, okay, then and it's aqueous, then what that means is I would have 1.0 molar of H plus ions and I would have 1.0 molar of Cl minus ions. So it's completely ionized. 100% of the molecule is ionized, okay, broken apart. What about something like acetic acid? So I'll write that down, HC3C. I'm going to write it down, sorry, a little different. CH3COOH aqueous, okay? And this acetic acid is considered a weak acid, which makes it a weak electrolyte, okay? And when acetic acid dissolves in water, it actually undergoes something that we call equilibrium. So it has these arrows here, okay? So let's see, the best way I can draw these arrows, let me do that again, okay? So I'm going to draw the forward arrow being really short and the backward arrow being really long. And we're gonna talk about equilibrium in Chem 110. The next semester, that'll be a big subject of this class, okay? So we'll discuss what that means in more detail in Chem 110, but what it means for us for now, that if I go and dissolve some acetic acid into solution, not all of it will dissolve. That's what this kind of arrow is representing. So only a very small amount of it goes in this forward direction, okay? And so that means the majority of it, this backward arrow is showing you that the majority of it remains unionized, okay? It can be dissolved, right? It can be a homogeneous solution, but when it's dissolved, the majority of it will not be broken apart into its respective ions. So for example, if I had 1 molar acetic acid and I then ionized it, I actually even have to add like several significant digits here to show the effect. Okay, so if I call this 1.000 molar, okay, once I dissolve this, okay, as it turns out, I would only have about 0.003 molar acetate and about 0.003 molar H plus, all right? Which means now, considering this, I would actually then have about 0.997 molar acetic acid remaining in the solution. And for my HCl, back to the strong acid case, this would mean that I would have 0 HCl bonded together. None of it would be bonded together. It would all have been dissociated, okay? Whereas the acetic acid, 1 molar of that would transform to about 0.997 molar would remain associated, bonded, and the very small fraction of that would remain unbonded, okay? So it still ionizes, but only partially. And this is the story, folks, between strong electrolytes and weak electrolytes. And we're going to see this manifest not only in strong acids, strong bases, weak acids, weak bases, but also in what we call soluble salts or insoluble or slightly soluble salts, okay? And so this picture, right, this kind of summarizes that demo. And the idea of this thing is that when you had a strong electrolyte, the light bulb lights up a lot more because there's a lot more ions to conduct that current. However, when you have something like acetic acid, the light bulb still lights up, but not as much, okay? And the picture doesn't do a great job showing that. So hopefully that demo really hits home, okay? So let's keep talking about acids and bases. So for the rest of just this lecture, I'm going to focus on acids and bases, okay? So there are several definitions for acids and bases. The first one we're going to focus on in this class is the Bronsted-Lowry definition, and that is an acid is a proton donor, a base is a proton acceptor. I want you to commit this to memory. An acid is a proton donor, a base is a proton acceptor. And when we're talking about a proton, specifically, we are talking about the H plus ion, right? If you recall, hydrogen as an atom, right, has 1 proton and 0 neutrons and 1 electron, okay? So now when you go and ionize this thing, when you remove an electron from it, literally the only thing you have, I wrote that backwards, literally the only thing you have is a proton, okay? That is acid. Acid is a proton. That's what's doing the corrosive acidic reactions we normally associate with acids, okay? So let's look at this reaction. Hydrochloric acid, HCl, a hydrogen bonded to a chlorine. Okay, that is the proton donor, so that is the acid. And now in this case, in this reaction, water has to be the base. Okay? And so as we will see, water can act as an acid and a base. It's very unique in that way. Okay? So now when this reaction goes, the acid donates a proton to the base accepts the proton, and what we are left with is this thing called the hydronium ion, H3O plus. It looks like this. It's an oxygen surrounded by 3 hydrogens, and it has a positive charge, okay? And then, of course, we're left with a chloride because the HCl bond broke up and gave us a chloride, okay? There's another shorthand way that we can write this reaction, and I'll show you what that is. I can write Cl gas, and I'm going to put the H2O liquid over the arrow. So this is kind of showing you so HCl exists as a gas in the absence of water, and we could bubble that gas into a container of water, okay? And so that's kind of what this is showing you without necessarily showing you the reaction to H2O. So we can say HCl gas dissolves in water, and that makes H plus aqueous plus Cl minus aqueous, okay? And in chemistry, this H plus, I'm going to put like a kind of equals sign. We often say that the H plus is synonymous with the H3O plus because technically, so let's say, technically, this is more correct. That's what's really going on in an acid, okay? It's not just a bunch of free protons floating around, okay? Because when water is present, water will absorb those protons because water is a proton acceptor. It's a base, okay? But when we write chemical reactions, generally it's okay to say H plus is the same as H3O plus. So this reaction is a shorthand way of writing this reaction, okay? So we can make these kind of shorter, more abbreviated versions of our chemical reactions, and we have to recognize that it does imply the same thing that this reaction is doing, okay? So keep both of those in mind. This is technically the full, complete reaction for an acid-base reaction, all right? But this one down here is also acceptable, okay? So just be familiar with both of those. Okay, moving right along. So now if we look at HCl, okay, still our acid, but now reacting with sodium hydroxide. Sodium hydroxide is a base, it's a proton acceptor, but as we will see, HCl, I've told you already, this is a strong acid. As it turns out, NaOH is a strong base. Water is not a strong base, okay, but NaOH is. And what makes NaOH a strong base is given by this picture right here, that when dissolved, sodium hydroxide will completely ionize into sodium plus and hydroxide, OH minus, okay? So now if we react this acid and base, check out what's going to happen, okay? We can see that there's an Na and a Cl, and they combine to make Na and Cl, right? This NaCl aqueous, okay? So what's happening to this H plus? Where is it going? Well, as it turns out, it's the hydroxide that's the base, okay? That's really what has the basic or even alkaline properties. So this hydroxide is absorbing this proton, and look at what the outcome is. H2O, right? When we have this OH, okay, minus, and this H plus, right? They're like little peas in a pod, okay? They combine to make H2O, okay? And so now what's also important to note, all right, sodium chloride is also a strong electrolyte. I'll just write strong electrolyte. So that means sodium chloride also is completely ionized. So what it means when I'm writing out this full reaction, and I've broken it apart in the ions, okay? Look, I've got chloride on the left side of this reaction, and I've got chloride on the right side of this reaction. So just like in a mathematical equation, when the left side equals the right side, they cancel out. And look, I've got sodium plus on the left side of the reaction and sodium plus on the right side of the reaction. So another acceptable shorthand way of writing this reaction, which is the reaction of any strong acid with any strong base. So let's say any strong acid plus any strong base always yields the following shorthand. I'm going to give it another name soon. I don't want to confuse you too much yet. For now, let's just think of this as a shorthand reaction, abbreviation or something like that. We actually call it the net ionic equation. I'm going to introduce that shortly. Okay? But any strong acid with any strong base can be abbreviated by writing H plus OH minus to make H2O liquid, and keep track of your phases. H plus is aqueous because it's charged. Hydroxide is aqueous because it's charged. And water is always a liquid unless it's a solid or a gas. So water can't be aqueous, okay? It's a pure material, all right? So that means water has to be a liquid, solid, or a gas. So you're going to hear me say that all the time. Water is always a liquid unless it's a solid or a gas, okay? So it's not aqueous. All right, moving forward, okay? So here's a list of strong acids that I want you to know for this class. So remember these, commit these to memory, add them onto your flashcards, all right? So we've got hydrochloric, we've got chloric, perchloric, nitric, and sulfuric. These are the common strong acids that you will see in a laboratory, all right? And notice how I did all of these reactions. I kind of showed the reaction in that shorthand way where I put the water over the reaction arrow, and they all generate H+, which, remember, is really like saying H3O+. Technically is more correct, but it's okay to write H+. And now look what is also the other product of these reactions. It's always the anion of the reaction, right? So here is the chloride. Here is the chlorate. Here is the perchlorate, the nitrate, and this one, we haven't encountered this yet, but this is called bisulfate. So if I wrote SO4 2-, right? Let's see where I can do that. I'm going to do that over here. So SO4 2- is sulfate. But when we do these acid-base reactions, we actually just do it with one proton at a time. So you notice sulfuric acid is H2SO4. This means it is diprotic. Don't you love how we make up words in chemistry? So diprotic. So it has two acidic protons. As it turns out, only the first one is strong. So this ion right here, HSO4-, it's not 2- because it still has the one hydrogen attached, which is positively charged. That makes bisulfate. Okay? And so now what this, so really quick, I'll just show you the generic reaction, right? This is the generic reaction for all of these. And notice it's HA. That A stands for anion. Okay? So we can represent any acid reaction as the following. HA plus H2O makes H3O+. I'll put in parentheses H+, right? And A-, the anion. Okay? And so now here are the structures of all these acids that I showed you. And what I want to point out, it's always that hydrogen, right? This is showing you the bond that has to break. So this bond, these are all covalent bonds. Okay? And they actually then dissociate to give us these two ionic species, these two ions. So it's pretty cool stuff, right? Because think about it. If you look at all these structures, these are all non-metals. So technically, in the absence of water, these acids are all covalent. But as soon as we put them into water, they readily ionize. They dissolve and they ionize. All right? And so this is showing you all of those bonds that have to break. Like, for example, we know that nitrate is NO3-. Well, here's nitric acid. Okay, so here is the NO3- chunk, right? 1 nitrogen, 3 oxygens. And then there is that H+. Okay? Or like for a more complicated one like sulfuric acid, okay? This whole thing that I'll circle, that is the sulfate. That's the SO4 2 minus. And you can see to balance that 2 minus, there is actually these hydrogens that are bonded there. Okay. Same with the perchloric acid, right? Here is the perchlorate, right? The ClO4 minus, and there's that hydrogen bonded to it. Okay. So let's see, moving forward. So let's talk about bases now. So a base, a good definition is a soluble ionic compound that contains hydroxide. Okay. So keep that in mind, right? I just told you all those strong acids that technically in the absence of water, they are covalent. Okay. The strong bases, however, are ionic compounds because look, sodium is a metal, potassium is a metal, okay? So it's a metal bonded with a nonmetal, so that means it has to be ionic. And so now if you look at these examples, sodium hydroxide or potassium hydroxide, they dissociate to give you hydroxide. This ion right here, I didn't introduce that in the other slide, but these ions right here are what we call spectators. Okay, so actually I'll back up right here, right? All of these ions right here, these would also be our spectator ions. Spectator ions. So that means they're not really doing much. Okay, they're not really doing much chemistry. It's the H plus that's doing the chemistry in the case of acids, and it's the OH minus that's doing chemistry in the case of bases. So what are some other examples? Well, look, I'm going to pick up my book here. I should have had a table right in front of me. But look, so I'm going to highlight this very first row. Sodium, potassium, lithium, et cetera, et cetera, et cetera. Lithium, sodium, potassium, rubidium, cesium, francium, magnesium, calcium, strontium, barium. All of those are good spectator ions to make a strong base with. All right? So let's go through those examples. So lithium hydroxide, okay? Rubidium hydroxide. What about calcium hydroxide? Well, calcium hydroxide definitely, but I have to write it like this because calcium is 2 plus. Or magnesium hydroxide. That's another good strong base. But remember, because magnesium is 2 plus, I have to write it like that as well. Okay? So let me follow through my notes. So another thing that we say for basic, so it has these compounds are bases, they have basic properties, would be alkaline. And this has become a funny joke in the running years because I call students out for being basic. Ha 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 ha. Don't be basic, y'all. Be acidic or be alkaline. It's always way much more funnier in the lecture hall. So I'm going to call you out for being basic and you have to guess what I mean. Are you being a basic, right? Or are you just being alkaline? Okay, moving forward. So here's an example of a weak acid. So I already did this one, and here you can see I got those equilibrium arrows drawn. I just drew them both the same length, which is fine for now, okay? But now notice here, a weak acid is still a proton donor, okay? So we have to remember that acetate, right, is CH3COO minus plus H plus, okay? And it's this H plus that reacts with the H2O to make H3O plus and CH3COO minus, okay? So now when I go to write this reaction, so when I go to write the shorthand notation of this reaction, it's really important to note that I have to keep the CH3COOH together, even in my shorthand reaction that later I'm going to call the net ionic equation. I have to keep this together because since it's a weak acid, not all of it is dissociated. And in fact, the vast majority of it is undissociated. So I would write this shorthand, by dropping out the water, I could just say CH3COOH is in equilibrium or reacts to form CH3COO minus AQ plus H plus. Okay, so this is one example of a weak acid that I want you to know. All right. When we get into Chem 110, there's going to be tons of weak acids that we talk about. But for this class, this is the example of a weak acid that I want you to know. Okay, and then similarly for our base, a weak base example is ammonia. Okay, so I know that you all have dealt with ammonia at some point in time or another. I hope you have. I hope you've at least cleaned your bathroom once and you've got the ammonia spray. Okay, that's a weak base. All right, and so if we remember what our definition of a base is, it's a proton acceptor. Okay, so now when we see ammonia reacting with water, okay, in this case, ammonia is our base, and now water is our acid. Okay, so I mentioned that before, that water can act as an acid and a base. When you react water with an acid, water will act like a base. When you react water with a base, water will react like an acid. So what's it doing? Well, it's donating a proton to the ammonia. And now look what happens. So if I take one of these protons and I add it to NH3, it has to become NH4, but also I remember my protons are positively charged, so it has to become ammonium. So if I add a proton, not only am I changing the number of hydrogens, right, from 3 to 4, but I'm also adding that positive charge there. Let's erase that so later on when I export it, it looks clear, right? So you're adding an atom and you're adding a charge. And then now when we think, what happened to water? Well, if water is neutral, H2O, if I remove a positive charge from it, it has to become negative. And so it makes hydroxide. So we can actually see in this weak acid example, or excuse me, weak base example, there's two definitions going on. There's that the base is a proton acceptor. The ammonia is accepting a proton. But it's also, number two, making hydroxide. Okay, so that's pretty cool. So the other example that I want you to know for this class for a weak base is the following. And when we write this reaction, we usually always keep the water as a part of the reaction, because that intimately shows us how the water is transformed into hydroxide. Okay, so we make ammonium and hydroxide. So these are two reactions I want you to know for weak acids and weak bases. Okay, so now what happens? So, and this is one demo that the guy didn't do, but this is a demo that I always like to do live. So what happens when you react a weak acid with a weak base? Well, your intuition might tell you that, well, they're both weak, so not much is going to happen. But it's the opposite. Actually, when you react a weak acid and a weak base, you get even more ionization. So this gets complicated, so let's break it down, okay? So I'm going to change my arrow. So I'm going to use red for acids, and I'm going to use blue for bases, okay? And so here is my base. So I'm going to highlight all my bases so we can keep track. And I'm going to highlight all of my acids so we can keep track of those, okay? So now let's see what happens here, all right? So the acetic acid, so I know I wrote it down slightly different here, apologies. So the acetic acid, right, the proton goes to the water, okay? An acid is a proton donor, all right? So now my H3O plus is an acid, okay? So now what is going on here? So let's go back to the ammonia, okay? Well, my ammonia is accepting a proton from the water, okay? And then now it makes hydroxide, which is a base. Okay? So now what happens? Well, look, we have a very small amount. So I'll say, I'm going to go to black here. So we have a very small amount of the acetate. Remember, because this is a weak base, or weak acid, excuse me, so not all of it dissociates. So that's a very small amount, okay? And my NH4 plus, that is a very small amount as well, okay? But so now what happens is we've got this hydroxide, which is still very small. However, the hydroxide can now react with the acid, okay? It accepts a proton from the remaining acetic acid to make H2O and even more of this ion. And then the H3O plus, we got the H3O plus from up here, okay? It donates a proton to the ammonia to make even more NH4 plus, all right? So what we are left with at the end of the day when this reaction goes is ammonium acetate. Okay, so that's pretty confusing. I know that's pretty advanced stuff, but so this is what's happening with the weak acid and the weak base. We basically, I'm going to use the word titrate, and I'll introduce that to you next. We titrate out all of the H plus and hydroxide, and what we're left with is NH4. I'm going to write it differently, and I'll just put a parenthesis around it so it's not as confusing. What we end up with is ammonium acetate, cation, anion, okay? And it's dissociated completely. That's what the aqueous means, okay? Moving forward, I think this video is going a little bit longer than I want it to, but that's okay. We're doing good stuff. So I just used that word titration, okay? And so what a titration means is we are reacting acid and base to the point of neutralization. Okay, so I'll say neutralize. So we titrate out all the acid and base, or in other words, we convert all of the H plus and all of the OH minus into water. Now, this is, as I kind of briefly mentioned here, this shorthand, it's what we call the net ionic equation. We're gonna do a lot more practice with this, okay? Our molecular equation gives me those full formulas, right? So the H plus was from HCl, and the OH minus was from NaOH. We know the H2O remains, okay? And what we canceled out from the net ionic equation was this NaCl aqueous. So technically, when we react a strong acid and a strong base, when we titrate them, we end up with salty water. So salty water is our product of an acid-base neutralization. And by neutralization, we're saying the solution is no longer acidic nor basic. It's just salty water, salty neutral water, okay? So to do this type of titration, we add what's called an indicator. And that indicator will change color under a certain condition. And there are lots of indicators. There's lots of chemical indicators out there. If we choose the right one for the particular acid-base reaction we want, it changes color when the reaction is done. It's pretty cool, okay? I think I have that, yes, I have that going on here. So right now what we would have, for example, is suppose here that in this flask is my strong base. In this burette is my strong acid. And titrating is this process of slowly letting this acid drip into the basic solution, into the base solution, And then now this thing right here, this medicine dropper, that is my indicator, okay? And we usually only have to put a teeny tiny amount of indicator. And if that indicator were phenolphthalein, that's this pink indicator that would be a good choice specifically for the HCl NaOH reaction. So we'll say good choice for NaOH plus HCl. And it's, you know, there's like dozens, if not hundreds of indicators. And we have to look at charts and to see like for which reaction would I want to pick the best indicator. You're not there yet. We'll be there in Chem 110. We'll eventually introduce that concept in Chem 110. Okay, so this would be perfect. Just this ever so slight pink color for specifically this phenolphthalein would tell us that we have made H2O liquid and NaCl aqueous. So we've titrated out all the H plus and OH minus. This, too much. So we passed it up, okay? So this perfect condition right here that I'm showing you, this is called our end point, where the indicator has changed color. Let me see what my next slide is. Oh, I've got them right here. Okay, end point. The point reached when the indicator changed color. Okay, but it's important to know that that's different than the equivalence point. The point when the moles of added titrant is stoichiometrically equivalent to moles of substance being analyzed. What does that mean? Well, that means that I have added HCl and NaOH in a perfect 1-to-1 ratio. Because you notice from this balanced reaction, they are 1-to-1. So the equivalence point and the end point aren't always necessarily the same thing. But if you've designed your experiment correctly, they will happen at a very, very similar point. Okay? So if the titration has been done correctly and the indicator was chosen wisely, the end point and the equivalence point will be the same thing. Okay? And so now the last thing that I want to do here is the sample calculation. Okay? So this is stoichiometry. This is basically our reaction stoichiometry. Okay? So I'm going to walk you through this thing, what I'm doing here. Instead of playing the music, I'll walk you through what I'm doing in this calculation, and that'll be it for this lecture. Okay? So what volume of 0.1 molar HCl solution is needed to neutralize 25 milliliters of 0.350 molar NaOH? So I'll remind you that big capital M, right, means mole per liter molarity. Okay? So first we have to get a balanced reaction. So we can see that it's HCl reacting with NaOH to make H2O liquid and NaCl. So we're making salty water, okay? And the really important thing of doing this balanced reaction is that we can see it's a 1-to-1 ratio. That's what's important, okay? So now what we're going to do is first figure out how many moles I need. Because basically in this reaction, right, we need the number of moles of NaOH to equal the number of moles of HCl. So for a titration, moles of base must equal moles of acid, assuming that it's a 1-to-1 reaction. Okay, for now that's what we'll deal with, just these 1-to-1 reactions. So I'm going to start by saying my 25 milliliters of NaOH, okay? Because when I have a volume and a concentration, that will give me moles. Volume, concentration gives me moles. Watch, check it out. I can say 25.0 milliliters of NaOH. I'm going to convert this to liters because I have the molarity thing going on. So I'm going to say 1,000 milliliters are in 1 liter. And this is how I can use this molarity, right? Check out how this works. Because I know it's moles per liter on top and bottom, and I really need liters to cancel. That 1 liter is 0.350 moles of NaOH. Okay, that's what that means. So when we see 0.350 m, you should be thinking 0.350 moles in 1 liter. Okay, and so now when I'm just going to do this calculation to show you what I get. Okay, so when I go and do this, here we go. Let's say 25 times 0.350 equals 8.75, and then divide by 1,000, and I get 0.00875 moles, technically, of just hydroxide. It's NaOH as well, but really it's the hydroxide that we want. And I also want to point out, we didn't have to use molar mass. Keep that straight. I did not have to use molar mass because I had a volume and concentration. Okay, when you think volume, concentration, I don't need molar mass, sweet. Okay, so now what is all this saying? Well, now I'm going to start with this number, and I'm going to say 0.00875 mole. I wrote OH minus or NaOH, right, depending on how you wrote the reaction. We'll stick with NaOH to be clear. So 0.00875 moles of NaOH. And now I'm going to use a balanced reaction. And the balanced reaction tells me 1 mole of NaOH reacts with 1 mole of HCl. Okay? And now I have to convert that mole of HCl into liters. Well, look, I have a concentration of HCl, 0.1 molar HCl. So I can use it the exact same way I did here, but now I'm going to flip it. Okay? So now this has to be 0.100 mole of HCl in 1 liter of HCl. And the problem asked me for what volume, so I could leave it in liters if I want. But look, they gave me 25 milliliters up here, so to me I think it's more reasonable to then make that a milliliter so that we're comparing apples to apples, right? So now I've got 0.00875. I left that number in my calculator so I wouldn't screw up the sig figs. And now all I have to do is take that number times 1,000 milliliters and then divide by 0.1, and I get 87.5 milliliters of my HCl solution. So what this means now, back to this original problem, okay, if I had, let me write this again, HCl plus NaOH. So if I had a 0.100 molar solution and 87.5 milliliters, and here I had a 0.350 molar sodium hydroxide solution and 25.0 milliliters, then I would perfectly titrate or neutralize the acid and base, and all that I would be left with is salty water. Okay, it would be neutral. No more acidic or basic properties. It would just be salty, neutral water. Okay, that is it for this video. I hope I stuck within my time frame. I didn't put a clock on, but I will for the next one. Okay, folks.